Okay, let's dive into this. Because today in this explainer, we're tearing into the core principles of passive house design. Now look, I know a lot of you already follow sustainable architecture closely. You totally get the basics of green building. But passive house, it takes sustainability to an absolute extreme. It's almost obsessive-level engineering, honestly. We're not just talking about slapping some eco-friendly materials onto a standard build and calling it a day. No way. This is a rigorous, science-backed standard that fundamentally flips the thermodynamic performance of a building on its head. We're going to explore the hardcore physics, the advanced materials, and the sheer structural exactness required to hit a standard so strict it literally redefines how we interact with the built environment.
So, think about this for a second. Can a house actually heat and cool itself? I know, it sounds kind of like a theoretical concept, right? But we're looking at the actual engineering reality behind a home that stays at perfect baseline comfort year-round, completely independent of those massive, noisy, high-load HVAC systems we're all so used to. When you actually apply advanced building physics, you can shift the entire climate control burden away from mechanical intervention and put it squarely on the architectural envelope itself.
So, what exactly is a passive house? Simply put, it's a comprehensive design standard that relies on smart building geometry, extreme insulation, and absolute airtightness to maintain comfortable indoor temperatures with virtually zero active heating or cooling. It's a fundamental architectural standard, not just an add-on like solar panels on a roof. And for those of you familiar with standard building codes, the sheer rigor of this certification is just staggering. We're talking about insanely strict metrics here. Stuff like achieving an airtightness of 0.6 air changes per hour at 50 pascals of pressure. Plus, there are hard caps on specific space heating demands, usually around 15 kilowatt-hours per square meter per year. It demands a level of precision that dictates your entire architectural strategy from literally day one.
To really grasp why these rigorous standards are absolutely crucial, we gotta look at the systemic flaws of traditional construction. Let's be honest, the standard homes most of us live in suffer from massive energy waste and super leaky building envelopes. They rely on these brute force feeding and cooling systems just to constantly compensate for thermal bypassing and vapor drive. It's a constant battle. But in stark contrast, a passive house operates as an ultra-efficient, rigorously airtight envelope with minimal energy requirements. By shifting from a reactive mechanical system to a proactive structural one, the building itself basically becomes the primary regulator of its own internal environment.
So here is the ultimate architectural blueprint we're about to build together. We'll cover the passive house concept, super insulation, high-performance windows, heat recovery ventilation, eliminating thermal bridges, and finally, the big picture impact.
Let's start with part one, the passive house concept and the core anatomy of the building.
The entire philosophy here really just relies on the thermodynamics of a high-quality thermos. Think about it. A good thermos keeps your hot coffee hot and your cold drinks cold completely without relying on a battery or some internal heating element, right? Well, a passive house leverages this exact same principle through thermal mass and strategic phase change materials. Rather than fighting off all the internal heat loads from your appliances, your lighting, and even just human bodies, the house actually captures and utilizes them. It mitigates exterior extremes by using the building's own structural density to naturally trap, store, and regulate temperature. The result? A perfectly stable microclimate inside, no matter how crazy the weather gets outside.
Moving on to part two, super insulation, or what we like to call the building's thermal blanket. Okay, so to actually achieve that thermos effect we just talked about, we have to engineer a continuous insulation layer, use draft-free construction techniques, implement advanced moisture control, and guarantee absolutely unbroken vapor barriers. These overlapping systems are so critical, and they have to work together in perfect harmony. You're not just stuffing some fiberglass between studs and hoping for the best. You're designing a continuous thermal wrap that explicitly prevents both vapor drive and thermal bypassing. By precisely calculating dew points and integrating really smart vapor retarders, engineers ensure that moisture literally cannot condense within the wall assembly. The end result is this sealed, high-performance fortress that completely isolates your interior climate from exterior temperature swings. No energy escapes, period.
Which brings us to our third pillar, high-performance windows, acting as active solar generators.
Now, what's really interesting about this is how dramatically the evolution of glazing technology shifts a window from being a thermal liability into a net positive energy asset. Think about standard double-pane windows with those cold, conductive frames. They're basically giant holes in the wall, massive weak points in a building's envelope. But passive house architecture completely reimagines this. It utilizes triple-pane, argon, or krypton-filled glass seated within highly insulated, thermally broken frames. And when you combine that with precise climate-specific solar heat gain coefficients,
These windows literally stop being passive energy drains. Instead, they act as active solar generators. They're specifically calibrated to harvest and trap that low-angle winter sun while completely deflecting harsh summer radiation. It's a total game changer.
Let's look at part 4, heat recovery ventilation, the vital lungs of the building.
Now, a lot of people think an airtight house would feel incredibly stuffy, but actually, managing indoor air quality here is an exact science, thanks to the Heat Recovery Ventilator, or HRV. This system operates as a continuous, perfectly balanced cycle of airflow. Let's walk through it. Step 1. Stale, moisture-laden interior air, which carries all that ambient heat from your daily living, is exhausted outward. Step 2. As it passes through a highly engineered heat exchanger core, the system meticulously extracts the thermal energy from that outgoing air. Then, Step 3. Fresh, filtered outdoor air enters the house and absorbs that extracted heat. These advanced cores can recover up to 90% of sensible heat. And the truly brilliant part? The stale and fresh air streams physically never mix, only the thermal energy gets transferred. So you're getting constant, pre-warmed, purified fresh air without the massive energy penalty of having to heat it from scratch.
Moving on to part 5, eliminating thermal bridges, which is a crucial technical hurdle.
I know you're likely already familiar with the baseline definition of a thermal bridge. It's that poorly insulated structural pathway where heat just easily bypasses your insulation and transfers directly in or out of the building. But the real challenge in passive design is exactly how engineers completely eradicate them to ensure that thermoseal we talked about remains totally unbroken. We're talking about utilizing specialized load-bearing thermal breaks under heavy structural elements like steel columns or concrete balconies. We're deploying continuous exterior insulation wraps that guarantee not a single stud or joist connects the interior directly to the exterior. It demands exhaustive, meticulous thermomodeling during the design phase, just to guarantee that the building's structural integrity never, ever compromises its thermal barrier.
Finally, let's wrap up with part 6, the big picture impact, and what this all means for superior living.
So the crucial point is 90%. That is the absolutely staggering heating and cooling energy reduction a passive house achieves compared to a typical code-compliant building. 90%. But let's zoom out for a second and look beyond just a single home. Imagine the compounding macro effects of a 90% reduction in space conditioning energy if we adopted this at a neighborhood scale, or, man, even a city-wide scale. We are looking at a massive drop in grid strain, dramatic reductions in peak load demands, and a profound decrease in overall carbon emissions, all while fundamentally upgrading the baseline comfort, the acoustics, and the air quality for the people actually living inside.
To sum it all up, Passive House Design transforms technical building standards into the ultimate blueprint for a fundamentally better, more comfortable, and sustainable future. It really is the undeniable future of sustainable architecture. So I'll leave you with this question. How can you apply these principles to your own living spaces? Consider the exact space you're sitting in right now. How does its current architectural environment compromise its thermal integrity? Where are the thermal bridges secretly hidden in your framing? And how are the existing glazing systems impacting your immediate comfort and your energy load? Start analyzing the blueprint of the spaces around you through the lens of pure building physics, and you might just see your home in a completely different light.